Hi there, welcome back to this channel. In this video, we are going to be talking about the electromagnetic waves. I will covering topics or subtopics like the visible light spectrum, the Newton's color disk or the Newtonian color disk, and the dispersion of white light. Now, what is dispersion of white light? Now, dispersion of white light is simply the separation of white light into the various colors or the various wavelengths of light that it contains. All right, now, what is the visible light spectrum? Now, we already know that the electromagnetic waves comprise of the following: the radio wave, microwave, the infrared ray, the visible light, the ultraviolet, the X-ray, and the gamma ray. Now, and we said that all of this represents the electromagnetic waves, basically made by the by oscillating electric and magnetic fields. All right. So, but we do know that even in the spectrum of that electromagnetic waves, we know that there is a small band that represents the white light band that represents the visible spectrum, the visible spectrum. So, and this visible spectrum is the one that the spectrum, the part of the electromagnetic wave or of the electromagnetic wave spectrum that our retina can detect or that can be sensed by our retina, because we have receptors in our retina that is capable of sensing this spectrum of light. Now, it is this visible light spectrum that we are going to be considering here. Now, this visible light spectrum ranges from a wavelength of about, you know that the wavelength increases in this order. So the wavelength increases in this order, and wavelength increases in this order, and frequency increases in this order. All right, so this guy has the lowest frequency, highest frequency, lowest frequency, highest wavelength. Is that okay? All right, now. So the wavelength of the visible light spectrum ranges from 700 nanometers to about 400 nanometers, all right? And this wavelength is basically 7 by, nano, the word nano means times 10 to the power minus 9. Is that okay? All right, I'm going to give us a list of those acronyms in a short, basically in the next video. And so this represent, if this is 700 nanometers, that is 7 by 10 to the power minus 7 meters, that is. All right. So this very tiny band is comprised of different wavelengths that represent different colors of light. And these several colors are affectionately known as the Roy-Beeve spectrum. The Roy-Beeve spectrum represents, refers to the red, orange, yellow, green, blue, indigo, and the violet light. Now, so it means that below this red light is what we have here, which is the infrared. So the word infra standing for less or below. And after the violet, we have the ultraviolet. Ultra meaning that it is higher than violet. Is that okay? All right, so we have the ultraviolet after this. Now, what we have here is just the order of their their wavelengths and frequencies as well. Now, and it is this wavelength that our eyes are able to perceive as colors. Our eyes are able to perceive as colors. So Newton was the first to tell us that when light is incident on a prism, the prism is able or is capable of dispersing this light, that is, splitting this light into the various wavelengths that it comprises of. So, and that is visible in when you shine light into a prism, you are going to notice some form of dispersion, and that dispersion into the several colors. Those several colors represent the spectrum of the visible light. So there is another spectrum of that band, of that little short band of visible light, which is the Roy-Beeve spectrum. Now, you see, let's talk about the Newton color disk now. The Newton color disk is he used it to prove the fact that all of this together um, are the only colors we have, and I mean there are colors in between all of this, but like they are the main colors that we have, and that they are the ones that come together to give us the white light. So, and Newton posited that white is not a color. So white is not a color, and black as well is not a color. So white is not a color, that is, at least in the sense that it is not a part of the spectrum of visible light. So it is not a part of, it's not characterized, it doesn't have, there's no wavelength of the visible light spectrum that is characteristic of white. And if you see that, there is no W there. All right, so, and Newton showed that it is a blend of all of the 7 colors that gives us the white light that we perceive with our eyes. So it means that white light is a blend um, um, of the polychromatic light. So we call light that has different wavelengths in it, we call it polychromatic. Polychromatic. Poly for many, chromo for color. So anytime you see in science the word chromo, it stands for color. So you see words like chromosome, stained body, it is stained heavily. I mean, it is going to be colored when stained, all right. So, but basically, I'm saying that Newton, I'm saying that white is not a color, and that it is a blend of many, that is a blend of all of these colors that gives white light. And how did he prove that? Now, he made what is known as the Newton's color disk. Now, the Newton color disk is basically a circular disk to which he made a pivot in the middle, and split the area, the surface area of this thing, into the 7 colors that we have. 1, 2, 3, 4. Oh, that's too much. Okay, so we have 1, 2, 3, 4, 5, 6, 7. All right, so we have R, O, Y, G, B, I, V. All right, so, and when he divided it into the 7 layers, he spun it around and at a very great speed. And at that very great speed, it was noticed that as the disc spun at a very great speed, it exhibited gray to white light. So, and this was how he proved that, and you can try that. If you have a disc and you color it red, orange, yellow, green, blue, indigo, and violet, and you are going to, at the end of the day, see white light band, the white light. So we know that when you spin it around, you saw that it appeared gray to white, which proved that the polychromatic light the white light is a polychromatic light that was a blend of all of the 7 colors, and also black is not a color, because black also it is it is in the sense that it's not characterized. There is no wavelength that's characteristic of black. So what you have is blue here. The B here represents blue. Right now, what black is the absence of any of the color wavelength. So when you're in the dark room, everywhere appears dark because there is no white light. There is no light at all hitting your eyes. All right. Okay, so that is what black is. Black is not a color, and white is not a color. All right. Now, we have the dispersion of light. Now, when light is dispersed, now how does it happen? First, one of the practical or natural evidence of dispersion of light is the rainbow. And what is the rainbow? It's just a band of the 7 colors that is formed in the sky, especially during the rain or immediately after the rain. So what happens is that when white light is shown on it, now the light as it enters into that cloud of water that still contains water droplets, the light becomes dispersed because of refraction. So as it enters into that cloud of droplets of water, it becomes refracted. It is refracted or deviated. all right, such that, first, in manner of deviation, there is also um, the level of deviation. The least deviated is the red, and the most deviated is the violet. All right. So rainbow is formed because there is that deviation, there is refraction within the layers of light. And what is refraction? The change in direction of light or wave as it moves from one medium to another of different densities. Now optical densities, because we talk about light. All right. So because as it moves from air, the surface of the air into the water, in the water it gets refracted because the optical density of water is higher than that of air. So because of that, it gets diffracted, and the different droplets form the different bands of light. So it is the different band of light up. So they just form the different band of light because of deviation. All right, that's just what rainbow is. Do you understand? So that's a physical example of refraction, of dispersion of light in real life. Right now, we now talk about the different spectrums that we have. There are two types of spectrum that we have, or the different spectra that we have. There are two types of spectrum. We have the pure spectrum and the impure spectrum. Now, the pure spectrum, we said spectrum is formed when a prism, when light is incident on the prism, and then you're going to see the refraction first, then the dispersion of light. We're going to see the dispersion of light. So refraction, because there is a change in direction or change in speed, all right, and that is also because there is a difference in speed. The light of the different wavelength travel at different speed within the medium. All right, so in this medium, light is traveling, this prism is going to travel at different wavelengths. So because of that, it becomes deviated, and because of that, by the time it goes out, the deviation also continues. All right, it is deviated into the red, orange, yellow, GBI, and V. All right, so you are going to see that red is the least deviated, with violet being the highest deviated. Now, the other thing you should notice is that, now what you should know is that this is an impure spectrum. Why is it an impure spectrum? It is formed when there is no distinct deviation, there's no distinct separation between the different colors of this light, of this white light. Now, if you want a pure spectrum is one that has a distinct separation of the polychromatic light. So, and how do you make that? You by the time the light is shown from the source, the light coming from the source that is incident on the prism is first made to pass through a convex lens. And then, what does the convex lens do? The convex lens is a lens that converges. So what it tries to do is focus the image on the prism, so that as the image is focused on the prism, it is going to be refracted perfectly within the prism, and at the time it emerges from the prism, at here you also put a convex lens so that it is also focused and that it is deviated perfectly. All right, so there is going to be a distinct separation in here. So we have a pure spectrum here. So a pure spectrum is formed when you have two convex lenses between the source and the prism, and between the prism and the detector. All right, so there is a detector here, of course, that on which you will read or see the band of 7 colors that are formed here. So that is pure and impure spectrum. All right, then we're going to see the color addition and color subtraction in the next video. Do well to subscribe to the channel. I'm going to link all those videos in the description below. See you next time. Thank you.